Hello everyone, myself Ananya Nambyar from RI Mysore pursuing my MSc degree in physics. Today I'm here to talk about the structural features of nanomaterial. And in today's discussion we'll be seeing how the structural features of the nanomaterials influence the property of them. So to begin with, we'll find what is actually meant by nanomaterial. So what is meant by nanomaterials? Nanomaterials are usually considered to be the materials with at least one external dimension that measures 100 nanometers or less, or with internal structures measuring 100 nanometers or less. They may be in the form of particles, tubes, rods, or fibers, as you can see. In the picture shown here, we can see the carbon dots, the graphene sheet, and fullerenes, which is a 3D structure. In nature, the volcanic ash, combustion product of forest fire, ocean spray, etc. are the natural source of nanomaterials, or we can say they are the natural examples of the nanomaterials we can observe. Other than that, the human-made nanomaterial range include quantum dots and carbon nanotubes. So now let us ask some questions. We have been discussing about what is nanomaterials. Now, what is so special about these nanomaterials? And which branch of science study the synthesis and application of nanomaterials? Or why do nanomaterials have different properties from their bulk? So let's find out the answer for all these in today's discussion. So now let's see what is a branch of science that deals with the study and synthesis of nanomaterials. Nanotechnology. Nanotechnology refers to the branch of science and engineering devoted to designing, uh, producing, and using structures, devices, and systems by manipulating the atoms and molecules at the nanoscale, that is, having one or more dimensions of the order 100 nanometers. In the natural world, there are many examples of structures with one or more nanometer dimensions, and many technologies have incidentally involved such nanostructures for many years, but only recently has it been possible to do it intentionally. Many of the applications of nanotechnology involve new materials that have very different properties and new effects compared to the same material made at larger sizes. The reason for this will be discussed in further slides. The application of nanotechnology can be very beneficial and have the potential to make a significant impact on society. Nanotechnology has already been embraced by the industrial sectors such as information and communication sectors, but is also used in food technology, energy technology, as well as in some medical products and medicines. Nanomaterials may also offer new opportunities for reduction of environmental pollution. Engineered nanomaterials are designed to take advantage of the unique properties exhibited by molecules at the molecular level in nano range, which are generally not observed in the bulk form. For example, the electrical conductivity of copper. The electrical conductivity of copper is very minute when it is in its bulk form, but very high when it is in its nano form. The changes in mechanical, electrical, magnetic, optical, thermal properties, etc. are studied and made use in the synthesis and application of these engineered nanomaterials. What is structural features of nanomaterial? Structural features of nanomaterial refers to the physical characteristics and properties at the nanoscale level. Here we will be discussing about the size of the nanomaterial, shape of the nanomaterial, surface area of the nanomaterial, the crystal structure, defects and interface, and the porosity of the nanomaterials, and how these influence the properties of the material in whole. To begin with, we will be talking about the size of the nanomaterial. At the nanoscale, the quantum effects become more pronounced due to the increased importance of quantum mechanics over classical mechanics. As the size of the particle approaches the scale of fundamental physical constants such as de Broglie wavelength and Bohr radius, quantum phenomena start to dominate. The first property that will be affected is the quantum confinement. In nanomaterials, electrons are confined within dimensions comparable to their wavelength. This leads to discrete energy levels and the quantization of energy states, resulting in electronic properties. For example, in quantum dots, the confinement of electrons can give rise to discrete energy levels and tunable optical properties. Second is the tunneling phenomenon. The quantum tunneling becomes more significant in nanoscale structures. Particles can penetrate potential barriers that classical physics would deem impenetrable, allowing for unique electronic transport phenomena. The quantum coherence. Nanoscale system can exhibit quantum coherence where particles exist in superposition state and maintain quantum entanglement over longer distance. This can lead to novel properties in quantum computing and information processing. Now we see how the shape of the material influences the properties. To begin with, we'll discuss with the surface area. As we know, different shapes result in variation in the surface area to volume ratio. High surface area enhances the reactivity and can impact the properties like catalytic activity, adsorption capacity, and chemical reactivity. Second is the electron mobility. The shape affects the arrangement of atoms and electrons. For example, in nanowires or in nanotubes, the elongated structure can enhance electron mobility, making them suitable for application in electronics and sensors. Third is the optical properties. The shape of nanomaterials can strongly influence their optical properties. For instance, the gold nanoparticles of different shapes, that is, in spheres, rods, and cubes, exhibit distinct absorption and scattering spectra due to the surface plasmon resonance, which is called LSPR. As you can see in the figure, the nanosphere, nanostar, and nanorod of gold show different absorbance spectra and LSPR. Nanoparticles with different shapes can exhibit varied magnetic behavior. As we know, anisotropy refers to the directional dependence of materials' properties. For instance, elongated or anisotropic shapes may have preferential magnetic orientation. Different shapes may lead to variation in the arrangement of magnetic moments within the material, affecting its overall magnetic property. The shape can influence the formation of magnetic domains within the nanoparticle. This, in turn, affects how the magnetic moments are aligned and interact with each other. For example, magnetic nanotubes may have different magnetic properties than spherical nanoparticles of the same material. Further, we'll talk about the surface area of nanomaterials. The surface area of nanomaterials significantly influence their properties due to the increased prominence of surface effect at nanoscale. First, we shall talk about the reactivity. As the surface area increases, the number of exposed atoms and molecules are also increasing. This heightened reactivity is particularly crucial in catalysis, where nanomaterials with high surface areas can exhibit enhanced catalytic activity due to more available active sites. Second comes the adsorption capacity. Nanomaterials with large surface areas have greater capacity for absorbing molecules onto their surface. This property exploited in applications such as gas absorption, water purification, and drug delivery. Third, we'll discuss about the electronic properties. The surface of nanomaterials often governs their electronic properties. Quantum effects are more pronounced at the surface, as we have already discussed, leading to the changes in electronic structure and the conductivity. Quantum dots, for example, exhibit size-dependent electronic properties influenced by their surface area. Now, biological interactions. In biomedical applications, the surface area of nanomaterials influence their interaction with the biological system. Higher surface area can enhance cellular uptake, bioavailability, and interactions with the biomolecules. In the next slide, we shall see what is the role of crystal structure of material in changing the properties. To begin with, we talk about the electronical properties. The arrangement of atoms in the crystal lattice directly affects the electronic band structure of nanomaterials. Variations in bins in this band structure can lead to difference in conductivity, band gap, and other electronic properties. For example, the semiconductor nanoparticles with different crystal structure may exhibit distinct electronic behavior. The optical behavior. The crystal structure influence the optical properties of nanomaterials affecting absorption, emission, and scattering of light. This can be seen in details with the spectrum of different examples. Quantum dots with specific crystal structure, such as zinc blende and woodside, can exhibit different optical behavior. Nanomaterials with different crystal structures may have varying mechanical properties. The arrangement of atoms in the crystal lattice dictates factors like hardness, elasticity, and tensile strength. For instance, carbon nanotube can have different mechanical strength depending on their catalytes and structures. Now we'll see how the crystal structure influences the magnetic and chemical properties. In magnetic nanomaterials, the crystal structure can dictate the magnetic behavior. For example, iron oxide nanoparticles can exhibit different magnetic properties depending on whether they have a magnetite or magamide crystal structure. The surface reactivity of nanomaterials is often influenced by the crystal structure. Exposed crystal facets and the surface energies play a role in determining the material's chemical reactivity and the interaction with the surrounding environment. Defects and interfaces in nanomaterial can significantly influence their properties, often introducing unique characters not present in the bulk materials. So in next slides, we can discuss how the defects and interfaces influence the properties. We'll see how electronic properties and mechanical properties are influenced by the defects and interfaces. Defects such as vacancies or dopants can introduce localized electronic states within the band gap affecting the material's conductivity and the two electronic structures. Interface between different materials or phases can lead to energy band alignment, influencing charge transport in heterojunctions. Defects can act as stress concentrators, affecting the mechanical strength and integrity of nanomaterials. Interface, especially in nanocomposite, can enhance or diminish the mechanical properties based on the bonding and interaction between the different materials. Chemical reactivity of nanomaterial. Defects often increase the surface reactivity of the nanomaterials. Interfaces between different materials can create opportunities for unique chemical interactions, impacting the reactivity in catalysis, sensing, or other chemical processes. The defects and interface can alter thermal conductivity in nanomaterials. Point defects and dislocations can introduce phonon scattering, influencing thermal transport. Interfaces in nanocomposites may impede or enhance thermal conductivity depending on the materials involved. Now we shall see how porosity in nanomaterials influence their properties in several ways. The surface area. Increased porosity leads to a higher surface area, enhancing the material's reactivity. This is particularly important in catalysis and adsorption processes. Mechanical properties are influenced when the porosity can affect the mechanical strength of nanomaterials. Generally, higher porosity may result in decreased mechanical strength due to the presence of voids and reduced material density. The thermal property are influenced by porosity, where higher porosity may lead to lower thermal conductivity, affecting their performance in thermal management applications. The porosity can influence the electrical conductivity of nanomaterials. It may introduce additional resistance or alter change transport pathways, impacting the material's electrical behavior. The density and mass transport. The porous structure can affect mass transport properties, influencing diffusion rates for gases or liquids within the nanomaterial. This is crucial in applications like filtration or drug delivery system. I hope that we have got the answers for the questions we had in the beginning. Nanomaterials are of so important as they give us different properties in, in their nanomaterial form than when they are in bulk form. This helps us to create more nanomaterials and make the life of humans easier. Nanotechnology has been working for the improvement and development of nanomaterials. We have seen how the structural features like size, shape, surface area, etc. of the nanomaterial influence the properties of the substance. I hope this talk was helpful for you all. Thank you.